Welcome. We are discussing multigrid methods for solving iterative matrix equations. What we have observed in last session is that convergence rate is slower if we have a large number of grid points, or if we have a large matrix compared to a smaller matrix in the same geometry. We have less number of grid points, and it is low due to the fact that large wavelength components of the error, which is required to smooth the solution for large number of mesh points, is very slow to converge. And what we are calling large wavelength relative to a particular mesh size, if we increase the mesh size, that becomes a smaller wavelength, and therefore, that converges fast, or that part of error is minimized fast if we use a larger grid point, or if you use a coarser mesh, larger grid spacing or coarser mesh. So, we came into a concept of geometrically looking into the matrix problem and reducing the computational steps by using multiple levels of grid. First, use a coarse mesh in which you solve the equations and get faster convergence, and then with that convergence the converged solution in the coarse mesh come to a final mesh, where again try to converge the equations, so that you get an accurate solution. So, this the particular technique we got discussed about the concept in last session, and the particular techniques we will look into will start from the multigrid concept, what is done in a multigrid method. So, in multigrid method we have several grids. Each grid differs from its coarser or finer grid by a factor of 2 or more or less number of cells, factor of 2 more or less number of cells in each direction. That means, if I have a mesh and I go to the coarser level, the coarser level will have half number of cells in that direction, and if I go to a final level, the final level will have double number of cells in one particular direction. Starting from a coarse mesh, we can construct number of grids increasing fineness. So, we will see it, but say I have a geometry where initially I have 4 points, this is the coarse mesh, and then I double the number of internal points. So, earlier there are 3 internal points, and then each or rather let us see that this is also 1 point. So, these are the ends. So, earlier we have 3 spaces, 1, 2, 3, 4 spaces and 3 internal points, and now we have all the older points will also be there. So, 1, 2, 3, 4, 5, 6, 7 points. So, we can construct the number of we can have a finer mesh by increasing fineness. We can inject more points inside and make the mesh more refined. So, the idea is first you solve in the coarser mesh, and then with this solution you interpolate it back to the finer mesh, take it as a guess solution and again solve it. The objective to use all these grids in a continuous cycling procedure such that the errors in the solution are resolved efficiently, and that is what we are trying to do. So, deploy several grids of varying fineness, solve low frequency errors of a given grid on coarser grid by restricting the error. Low frequency error in a given grid is high wavelength error on that grid, but solve that in a coarser grid by restrict the error in a coarser grid. So, it becomes a low frequency high frequency low wave number error in the coarser grid and can be solved fast. Prolong the solution to the grids. From the coarser grid solution, prolong it, interpolate it to the finer grid, so that the corrections can so that you can get accurate result on the finer grid. So, first solve it in coarse grid, which will be you will get a faster solution, then take the coarser grid solution, prolong to fine grid. The component the multigrid technique consists of these few steps. Detect what is high frequency and what is low frequency by looking into the grid size. So, you look into the grid size and find out that whether all the errors will be relatively of higher frequency or lower frequency. If the errors are of higher, most of the errors are of higher frequency. That means if the grid is coarse enough, you do not need to do any multigridding, but if it is smile enough, you have to do one level of multigrid. If it is very fine, you have to do multiple level of fine gridding, so that the largest wavelength error becomes somewhat well resolvable by the most coarser grid. It becomes small wavelength error compared to the coarse grid. So, detect the number of grid levels, and there are some mathematical prescriptions for that, but however, the application scientists do these things by their expertise and experience, check whether multigrid is required for this grid level and how many cycles of multigrids will be needed. Formation of multiple level of grids. So, once you have looked into the grid size, you now can form that what will be the different grid levels and form multiple levels of grid. Solve for high frequency errors which are large wavelength, high frequency, and solve for this will be solve for high frequency errors in coarse grid. This will be, just a second, solve for high wavelength error. This should be solve for high wavelength error. I will change it, which is low frequency. No, this is fine actually. I am sorry. Let me explain this. Solve for high frequency errors in the coarse grid. What is high frequency error in coarse grid? What is high frequency error? Is low wavelength error. Small wavelength errors are difficult to resolve. So, what is small wavelength error in a fine mesh will be large wavelength errors are difficult to resolve. What is large wavelength error in a fine mesh will be a small wavelength error in a coarse mesh, and therefore, it will be a high frequency error. So, first solve what is high frequency error in coarse mesh, and this is basically the small wavelength errors in coarse mesh and large wavelength errors in the fine mesh. This will be quickly solved. And then the there will be some low frequency residuals will be there, and that you have to take it into the fine grid and solve it. This residual is now low frequency to the fine grid, which is coming from the coarse mesh, which was high frequency error in coarse mesh. This again has to be resolved. So, it cannot be direct, everything cannot be directly solved in coarse mesh, you have to come back to fine grid also. Transfer the residual. These residuals are low frequency residuals in coarse mesh. You transfer them to the fine mesh, low frequency residuals in fine mesh, you transfer them to the coarse mesh, where they will be high frequency errors, and solve for them. So, there is a cycling between fine mesh and coarse mesh. Solve for corrections in coarser mesh, transfer the corrections to finer grid, and do a cycling till you get a convergence. So, the idea is now actually very simple. You solve the equations in coarse mesh, see what are the corrections in the solution variable, transfer these solutions variables into the finer mesh, update the solution at the finer mesh, and see whether you have got the residual right, residual rather. If residual is non-zero, you calculate the residual in the finer mesh, and this residual or the required correction for the residual in the finer mesh, this has to be again transferred in the coarse mesh, and there will be a coming down enough from a cycling from fine mesh to coarse mesh till you get a converged solution, and the converged solution must be available at the finest mesh, because we are trying to get the solution at finest mesh where the desired accuracy can be obtained. So, how will be a framework? So, we take 1D finite difference method. This is the coarse grid. We inject one point in between each, so you get a fine grid. The grid spacing is exactly half, number of if these are boundary points, number of internal points are actually doublet. Then you increase one more level of fineness, increase one more point here. So, what was a single spacing here, now this is there are 3 spaces. Now there are 4 spaces in between. So, each has been reduced by 1/4 times. You get a finest grid here. This is where I need the solution. I will start getting solution here, and then the solution that has been converged here, I will put it here and update the solutions. I will which will be converged here, I will put it here and update it fine. And now the update what I am getting here, that this will be the correction parameters here, I will pull it back. Because this is a difference matrix and difference matrix, earlier it was converged here, the new solutions will not appear to be converged here probably. So, I have to again do this rounds of iteration till I get a convergence. For a 2D mesh point, this is taken from Professor Demel's lecture notes in UC Berkeley. This is the finest mesh. So, from finest mesh we are going to the coarse mesh. The points where I have level 2 will be the member of the coarser grid. So, when we are solving in a coarser grid, we only solve in these points, we will not solve in the internal points. When we go to the coarsest mesh, the points labeled as 1 will be there. Now, if this is the geometry, I can see the coarsest mesh is just sufficient to resolve the entire boundary. There is one point in this boundary, one point in this boundary, one point in this boundary, one point is this boundary. 4 internal points except for the corners in the boundary. That is sufficient to resolve. There is a least number of points which we can deploy to get at least one internal point here. This is the coarsest mesh, and this is obtained by removing points from the finest mesh, and this is from fine to coarse sequence of the, this is the fine to coarse sequence of the meshes. The multigrid framework will be start with the coarse grid. The grid can be the coarsest one which is just sufficient to describe the boundaries with least number of solution points. So, earlier we have shown one of the coarsest mesh, only one internal point except everything is a boundary point. Refine the mesh by doubling the mesh points by inserting rejecting one more grid point between 2 consecutive points in each direction. And you can refine it to certain to few more levels, instead of one multigrid level you can use number of multigrid levels. Like last 2 examples we have seen has 3 levels, grid levels, 2 multigrid levels, one is the finest one and 2 more coarser levels. Final solution has to be obtained in the finest mesh only, and this is I am asserting it several times because we need the desired accuracy which can be obtained only with the finest mesh. Using this framework is named as geometric multigrid method because due to the fact that we are using a geometric framework to create the grids. We are not taking the matrix directly and seeing what can be done on it, what we have done in preconditioning technique. Rather, we are getting the geometric framework, getting a governing equation which is a differential equation, discretizing it, knowing the geometric framework and changing this geometric grid system by inserting more spatial points to make finer mesh or reducing more spatial points to make a coarser mesh. That is why this is usually termed as a geometric multigrid method. The main components of multigrid procedure is relaxation or iterative solution procedure on a particular grid level, restriction or transferring these errors from the final level to the coarser level, prolongation, correcting the finer grid solutions to using the coarser grid corrections, getting the corrections in coarser grid and transferring it into finer grid, and cycling, that means that the solution you obtained here is actually not a converged solution. So, you have to go number of steps till you get a converged solution at the finest grid level. Because if you want to correct the solution at the finest grid level, it is again a matrix solver which will have all the low frequency large wavelength components and will take lot of time. So, maybe you do few iterations in the fine grid level, only correct the use the coarse grid level corrections and correct some of the fine grid levels, and then go to relaxation where the main iterative solution procedure is run on the coarser grid level. Geometric multigrid solution is formulated for a solution of PDE in a different geometry. Let us consider an elliptic partial differential equation. L is a elliptic equation, like L is equal to say nabla square, something like that. L is a so this is a elliptic PDE which we are trying to solve. Why elliptic PDE? Because boundary condition in all domains are defined, then you can solve elliptic PDE. So, like a Laplace equation or a Poisson's equation. Let us think we are solving an elliptic PDE. When this equation we convert it into a matrix equation with discretization H, grid spacing H, we get a matrix. If we change, because we are discussing about different grid levels, if we change H to 2H or go to a coarser level, the matrix will be different. The solutions will also be a different vector. Solutions are member of Rn, that will be member of Rn by 2. Solutions are also different vectors, and the right hand side matrix will vector will also be different. But for one particular grid spacing, let this be the matrix solution, which we try to solve using multigrid method. We will calculate the residual vector after, say after jth iteration, the residual vector is Rj H minus H phi j. This residual is slow to converge. If I try to get the residual to be 0 by something like a Jacobi or a conjugate gradient method, this is a slow to converge method because it has low frequency high wavelength components. So, we transfer this residual to a grid level, coarser grid level, which is H minus 1 or twice H, one more coarser level of that. That is, the new residual is equal to the old residual multiplied with a transfer function. In this transfer function, so what we are doing is that the residual is calculated in this mesh. So, this is RH. We are transferring this residual into a new mesh. There one more point is needed. We are transferring this residual into a new mesh, which is RH minus 1. So, there is requirement of transferring this to this, this to this, this to this. So, one idea is to directly map it, but directly mapping might give us wrong solution, because this residual actually contains information from these two residuals also. So, something like a trapezoidal interpolation might be required, and this transfer function is called I H H minus 1. This might be a trapezoidal interpolation function, like this residual is actually formed. So, if this has a these are the values, this residual is actually formed using a trapezoidal interpolation of this. Something like this can be done. So, do an interpolation to transfer the residual at the final level to a coarse level. I is like an interpolation operation. This operation is called restriction. From residual from final level transferred to coarser level is called a restriction operation. Now, delta x, the correction vector xj minus x star, can be evaluated at the coarser level. So, solve the matrix equation at the coarser level, see what is the correction. This is called a relaxation operation at the coarser grid level or H minus 1 grid level. Now, so once this is done, the solution is in a sense obtained in the coarse grid level based on the guess solution that is coming from, and the residual that is coming from the fine grid level. Again, the residual at fine grid level, which is being restricted to coarse grid level, is not same with the residual which should have been evaluated if we are just solving the equation at the coarse grid level, because it contains information from the nearby points using, say we have used a trapezoidal rule. So, it has some of the high wavelength component of the error also. So, when we will solve it, we will get a solution which is not a right solution for the coarse grid level, but that has some, because that has some components from the finer grid levels. So, low frequency errors are less in coarser grid levels. These iterations will converge first, because the low frequency error has been converted into high frequency error by increasing the grid size. For desired accuracy, this will converge, but it will converge to a different solution, and we also need to compute the solution at the finest grid level H. So, the corrections that we have computed in coarser grid level are to be transferred to the finer grid level. IH H minus 1 is a projection operator, kind of inverse of the previous projection operator, but not exactly inverse for numerical stability issues. Is a projection operator which uses the solution variable which will be used to update the solution variable at fine grid level using the coarse grid level solution. So, this is calculated at coarse grid level, use this and this projection operator and calculate at fine grid level. So, what will happen, like you have these points and here you have calculated delta x H minus 1, and now this is your fine grid level. and here you update xh is equal to x j plus 1 is equal to xh j plus delta x h minus 1 into IH h minus 1. So, we get some of the effects from this to this particular correction value. So, the effect from here will come to this particular point, and then we will update the solution at this point. So, solution is updated here using the corrections, using the changes in the solution vector or the corrections which is computed in course level, and an interpolation like operation is done for that. This error is interpolated back to the fine grid level. This is called a prolongation operation. The error calculated at the fine grid, the correction calculated at the coarse grid level is transferred to the fine grid level, so that we can update the solution in fine grid level. Will this give me a converged solution? No, because we have calculated something in fine grid level which has looked into some of the low frequency oscillations in the coarse grid level, but has not resolved for all the high frequency oscillations here. So, we have to again do some correction at the fine grid level, and this is again like an interpolation from coarse level to fine level, this I operator. The updated solution calculated in the fine mesh level still considers some of the high frequency errors. High frequency means in between the two grid levels, the middle grid level we have used correction from prolongated correction factor from coarse grid level and put it here, which has not been resolved here. So, it still contains some of the high frequency errors, and the residual calculated with this will not be 0. So, the residual may be calculated at this grid level, and the same loop that this is transferred to the residual calculated to the fine grid level and transferred to the coarse grid level, and you solve the equations to the coarse grid level, this may be followed. So, the residual may be calculated at this grid level and will again be restricted to the fine grid level. And similar cycling from, this is called a cycling from coarse grid level to fine grid level, again taking the calculating residual at fine grid level, restricting it to coarse grid level, again solving here. This cycling operation can be converged, can be performed till we get convergence at the finest grid level, that is residual at the finest grid level is close to 0. So, the steps what we have discussed, that relaxation iterative solution procedure in a coarser grid level, restricting, then transferring, so or rather first iterative solution, sum of iterative solution procedure in a finer grid level, restricting it to coarser grid level, again relaxing here, the orders may be changed. So, converging, getting the updated solution at coarser grid levels, calculating the correction factors at coarser grid levels and correcting the fine grid solution using the coarse grid corrections, and then cycling, then again going to coarser grid level and doing it. The orders may change of relaxation and restriction, because in coarser grid, after you restrict in coarser grid level, you have to relax. So, this is the steps of a multigrid procedure. A number of grid levels can be used, and number of cycles of relaxation, restriction, prolongation can be, rather first restriction, then relaxation, then prolongation, that is the cycle that can be run till convergence. There are very well known V and W cycles. If we have one fine level, you go to the coarse level and again come back to fine level, and probably the solution has been already converged, that is called a V cycle. Or you again go back to the coarse level and follow this. So, coming from here to here, again coming from here to here, this is called a V cycle. There can be multiple levels and multiple grid levels, and there can be different V cycles, but the cycling pattern is same. You directly go from a fine level to the coarser level, go to the coarsest level, relax the solution here, and this is the restriction operation. So, this will be the restriction and this will be the prolongation, and this is the relaxation. There is another thing called W cycle, in which you can do relaxation. This is a relaxation, this is a relaxation, again this is a relaxation, this is not a relaxation. You go to a come to a coarsest mesh, do relaxation, solve the matrix equation, then correct it to a middle level coarse mesh through prolongation, and then you again restrict the solution to the coarser level, to the coarsest level, do a relaxation. This is a W cycle. There are multiple W cycles with different grid levels and different cycling. So, these are two commonly known cycles. V and W cycles are defined using grid levels and recycling, and the number of grid levels used and number of recyclings. V is for running single full cycle from fine to coarse, again fine to coarse, fine, and W is for multiple short cycles from finer to fine to coarser, and again coming back to fine, again going back to little more finer, again coming back to coarse. These are called W cycles. Both these cycles are used depending the applications and the type of matrix, the computational requirements, etc. Both these cycles can be used for different purpose. If I can define a W cycle or some cycle like this, in which going through one particular cycle will give me the converse solution, I do not have to recycle it several times. This is called a full multigrid method, which is little more complex method we are not discussing here. And the multigrid method is usually based on the geometric, what we have discussed is geometric multigrid method, geometric coarsening and fining of the mesh. But especially for unstructured mesh, and there can be different matrices also, which is not coming out of a Laplace equation or an elliptic equation in a defined geometry. There can be different matrices where geometric multigrid cannot be applied. Here what can be done is an algebraic multigrid procedure, that means take the main matrix, club few of the solution variables to one particular solution variable, like make a block and make it one particular solution variable and solve the equations there, and then prolongate it to the actual solution variable. So, there is a idea of algebraic multigrid. This is mathematically much more complex, but many solvers, there have been lot of developments using algebraic multigrid also. Here you do not need to know about the geometry directly. There are many commercial and open source softwares which already have coded the algebraic multigrid, and you can use it over your matrix solver, over the general matrix solver you are using. So, this is another way to look into the multigrid procedure. However, we are not discussing the details of the multigrid procedure due to short of time, because this is a course not on multigrid exclusively, this is a course on matrix solver. So, I tried to give some introductory concepts on matrix multigrid method, which is useful for rethinking matrix solvers, in which they can be redesigning the matrix solvers in a direction that they can give us first solutions. So, these are these two techniques we have reviewed on matrix solvers. One is the multigrid method, another is preconditioning technique, where given a matrix solver, given the for a particular matrix which is a large matrix and slow to converge, we can use these techniques over a given matrix solver and get faster solution. Okay, so, with this, I guess we come to the conclusion of the course. We started with discussing the basic properties of a matrix, then discussed about direct solvers like Gauss elimination, LU, TDMA type of solvers, looked into the cases where there are infinite solution and null space solutions are required to get a solution, where there is no solution and a best estimate can be obtained from normal solution. So, this what we looked into the direct solver method, and then we came to iterative solver, looked into a group of solvers called basic iterative methods, then came to projection based methods and Krylov subspace based methods, and also looked into the block matrix solvers as well as the parallelization strategies which probably can be craved out of the block matrix solvers. And then we looked into the methods for accelerating a matrix solver given a particular matrix which is slow to converge, which is preconditional, and another method is matrix solvers. This kind of summarizes the course. and it has been probably it will be of use to a larger community who will be using matrix solvers for their research and academic purpose. Hope I tried to convey the key points of matrix solvers, and hope this will be of use to this larger scientific computation community. Thank you all.